Okay, now we've looked at partial pressures when we were dealing with a mixture of gases, and you've read that your kinetic molecular theory says that components in a gas mixture act independently of each other. So the pressure due to any individual component is called as partial pressure, and the partial pressure of any component is that component's fractional composition times the total pressure. So if we are going to do the example of a mixture of helium, neon, and argon, it has a total pressure of 558 millimeters of mercury. That's our total pressure here. And the total pressure then will refer to the partial pressure of helium plus the partial pressure of neon plus the partial pressure of argon. Okay? And if we had more gases, we'll just keep on going. But in this case, we only have 3. So that's it. So all of these partial pressures should end up adding to 558 millimeters of mercury. Now we are told that the partial pressure for helium is 341 millimeters of mercury. And we are told that the partial pressure of neon is 112 millimeters of mercury. And what is the partial pressure of argon here? That is unknown, but remember we have the total. And this was a Dalton's rule of partial pressure. Okay, so that's Dalton's rule. So of course, if we have unknown, we'll just sum these up and subtract them from the other side. So 341 plus 112, that's 453. And we're just going to subtract that from both sides. So 558 minus 453, and we get the partial pressure of argon is going to be 105 millimeters of mercury, or argon. I wonder where I got mercury from. So that is argon. Okay? Now you go ahead and you give this a try. A sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 745 millimeters of torr, which is really the same thing as millimeters of mercury, right? So we have 745 torr, and we have the partial pressure of water and the partial pressure of H2, the hydrogen gas. And the water vapor pressure we find out is to be 24 torr, and we want to figure out what the partial pressure of the hydrogen gas is. So of course, then to figure out the hydrogen gas, you would have to do 745 torr minus 24 torr, and that will give you 721 torr for the partial pressure of hydrogen. So we found out about how our bodies kind of adapted to this 1 atm total pressure. And from that 1 atm total pressure, because we have about 20% oxygen in the air, we are used to a partial pressure of 0.21, let's convert that into a fraction, times the total pressure of 1 atm. So we are used to about 0.21 atm partial pressure of oxygen. And since our air is also 78% nitrogen, let's do 0.78 times 1 atm. That's approximately 0.78 atm. And that is our partial pressure of nitrogen. Our bodies got used to this. And we saw that if you go up, let's say Mount Everest, where the total pressure is 0.311 atm, we still have about 21% oxygen up there, but this translates to 21% of this translates to 0.065 atm partial pressure for oxygen, and we have this decreased partial pressure for oxygen, we've decreased the density of oxygen in the air. Because we've decreased pressure, we've decreased pressure, so we increased volume. Okay, and if we increase volume, remember that density is mass divided by volume. If you increase the denominator here, then what have you done? You've decreased density of the air. And that decreased density in air will result in less oxygen getting into your lungs. If you have less oxygen, you will get what we call mild hypoxia, which causes dizziness, headache, and shortness of breath, whereas severe hypoxia results if your partial pressure of oxygen drops below 0.1 atm. And this may cause unconsciousness or even death. So climbers, they want to take oxygen with them. Up there. On the other hand, you can have oxygen poisoning, believe it or not, oxygen toxicity. If you go scuba diving and you go down below to about 4 atms of pressure, so about 30 meters or so, this will result in a partial pressure of oxygen to be 0.84 atm, which is far higher than the ideal 0.21 atm. This increases the oxygen density in the air, and so you get a flood of oxygen into your lungs, and increased oxygen in your lungs results in what we call oxygen toxicity, leads to muscle twitching, tunnel vision, convulsions, and we warn divers not to venture too deep because of this result. Okay, so guess what? Just like we have adapted to having a partial pressure of 0.21 atm for oxygen, we've also adapted to having about 78% atm, or a partial pressure of 0.78 for atm for nitrogen. And guess what? When we go down again into the deep sea, this goes up at about 30 meters. The partial pressure of nitrogen becomes 3.1 atm. So we're increasing the amount of nitrogen in our lungs. And if we get used to this, or I'm sorry, if we get exposed to this, this is what we call nitrogen narcosis, or rapture of the deep. Divers describe it as being tipsy, and judgment may become impaired, and that you don't want to do if you're deep sea diving. That could also kill you if your judgment is impaired. So we need a special mixture, and this is pretty neat because we call this heliox. Heliox is a mixture of helium and oxygen, and usually at a smaller percentage of oxygen than what we have at the surface, typically about 2 to 5%, okay? So we would put helium in there instead of nitrogen to eliminate the risk of nitrogen narcosis, okay? But think about what happens to your voice. And actually, deep sea divers that work in conditions like for oil companies, they usually put them in deep sea conditions for about 20 to 30 day cycles, because they don't want to go through this gradual depressurization every single day. So they'll put people in deep sea for about 20-30 days, and they get some work done, and then they bring them up to the surface, and then they go in cycles. And those guys that breathing in this helium, when they talk to each other, they have the high-pitched sound that we usually do when you suck in the helium from a balloon. So that's the fun part about that. But at least it saves their lives, and it allows them to have good judgment and avoids narcosis, nitrogen narcosis. All right, so let's see how we can use this idea. All right, and let's calculate the partial pressure of oxygen that a diver breathes with heliox mixture containing 2% oxygen at a depth of 100 meters, where the total pressure is about 10 atm. Okay, so we have 2% oxygen, which means 98% is going to be from helium. All right? In other words, our total pressure is 10 atm, and so we want to calculate the partial pressure of oxygen is going to be just its percentage converted to a fraction. So we move the decimal place 2 places to the right. So that's 0.02 times 10 atm. Okay? And so that will be the partial pressure of our oxygen, which is 0.200 atm. And so, isn't this ideal? Because at the surface, remember, we're used to this. So this is actually pretty close, and we will put our bodies in a decent condition at 100 meters below water. Now, let us do another example. You try this one and then replay the video to see if you get this correct. A diver breathing heliox with an oxygen composition of 5% wants to adjust the pressure to get this ideal pressure of 0.21 atm. What must the pressure be? Okay? So, this time we have the partial pressure to be 0.21 atm, and we want to. So let's see. Now let's look at how we did this one. The partial pressure of oxygen, which we have this time to be 0.21 atm. We want to put the fraction of oxygen, which in this case is 0.05, times the total pressure, which is what we don't know this time. Okay? So let's do this on either side to get the total pressure. So 0.21 divided by 0.05. So he should adjust his total pressure to be 4.2 atm in order to get this ideal amount of partial pressure for oxygen. So your P total should be 4.2 atm. Now let's talk about this concept of when you, a lot of times in the experiment, in the laboratory, you'll do experiments where you collect hydrogen gas over water, and that gives you a certain pressure and at a certain water temperature. All right, and this is important because you actually will do that. If you go on to general chemistry, you're going to collect hydrogen gas over water. So I teach that to you now so that you understand it later, okay? Hydrogen gas was collected over water to give a total pressure of 758 millimeters of mercury, okay? Now, the temperature here was 25 degrees Celsius, the water temperature. What is the partial pressure of the hydrogen gas? Because now, remember, our P total, this is hydrogen collected over water, which means we're going to have partial pressure of hydrogen, but we're also going to have a pressure of water vapor, okay? So we have to, in order to figure out the partial of pressure of hydrogen alone, we have to do pH2. We got to take our P total and we got to subtract from it the partial pressure of water. Now, how do you figure this out? There's a table in your book, and if I give you this on a test, I'll provide this table. And you will look this up in the table, and it says at 25 degrees Celsius, your pressure for water is approximately 23.8 millimeters of mercury. Okay? And so, let's take our total pressure, 758 millimeters of mercury minus 23.8 millimeters of mercury. And so, the pressure of your dry hydrogen alone, without your water vapor, is going to be 758 minus 23.8. So it should be 734.2 millimeters of mercury. Okay? So that is how you figure out the partial pressure of hydrogen. It could be oxygen or anything if it's collected over water. The key point here is this sample was collected over water. So the water vapor contributed to the total pressure. But we don't want that. We want the pressure of our pure hydrogen alone without the water vapor. So we have to subtract the pressure of the water vapor from our total pressure.